Single particle in one dimension. This is an important topic in statistical mechanics, that what is meant by the single particle in one dimension. So we can conclude from the question, single particle means only in one axis. For example, we are taking a particle which is moving in x-axis, moving along x-axis or y-axis or z-axis. If we take only one side, for example, we take a particle along x-axis, then this will be known as single particle in one dimension. Further, when we move about this topic, we see about the definition of single particle in one dimension. So in simple terms, single particle in one dimension refer to a single particle like object that moves along a straight line or one dimensional path. As I already have told you that if a particle moving along only x-axis, then it has only one path or a single path, then this will be known as single particle in one dimension. So next is what is meant by single particle in one dimension is one dimensional motion can be defined in physics and objects motion can be described along only one axis, usually represented as the x-axis. This simplified motion is known as one dimensional motion. If we see about the particle representation, so this is very important how we can represent a particle in one dimension. So in one dimension, the object under consideration is treated as a particle. A particle in this case refers to a point like object with mass but negligible size. So this is very important to note that if a particle is moving only in one dimension on single path, then it has only mass but negligible size. This size will be very small or negligible. This is very important condition to study single particle in one dimension. So to describe single particle in one dimension, we use Schrodinger wave equation in one dimension. So this is the Schrodinger wave equation in which V into x is the potential energy, phi into x is the single particle wave function, and E is the energy. The particle is confined in a one-dimensional box of length L. So this one-dimensional particle is placed in a box and its all the values are given. Now we will move next and put the values and get our determinant. To study single particle in one dimension, we use this formulation in which wave function phi of n number of particle and its position. To study wave function of particle in one dimension, we use this formulation in which phi is wave function and n is the boundary condition whose values is positive and x is the along x direction is moving. So a is the constant. Here sign will taken because particle is moving along y-axis due to potential energy, because when a particle move in one dimension it has only potential energy, and in potential energy we take only height. That's why along y-axis we take sine theta. That's why here we use sine, and this is the formulation in which we put the value and get the value. The first boundary condition is automatically satisfied by such a wave function. The second boundary condition is satisfied provided n is a positive non-zero integer. Why do we exclude negative integer? So this is the question, why we exclude negative integer. So this question is for you. If you know about the answer, then leave your comment in section comment below. Otherwise I will answer you in the next video. If you did not understand about the negative sign as I told you earlier, so that's answer is here. We want independent solution of Schrodinger's equation corresponding to independent quantum state. So if we are not taking independent solution, then this is not possible. That's why we take a positive value, not negative value. For example, if n is chosen to be negative integer, then the wave function is linearly dependent on the wave function. So here is the dependent is the main property, but we want only independently on the wave function for the corresponding positive integer. It is not an independent solution. That was the reason which I told you earlier that we not take a negative value. That's why, for example, a wave function, if I here we take negative value, so put all the negative value, so its result will be the same as the wave function we take positive value apart from a minus sign. It is not an independent solution. That's why we not take negative value, we only take positive value. Previously, as I told you, we restrict the set of quantum state to those with n positive integers so as to ensure that we only consider independent quantum state. So to show independent quantum state, we take only positive value. If we are not showing independent, if you want to show only dependent quantum state, then take negative value. As we already studied about the particle wave function, but here we will study about the energy of wave function, which can be represented by En. This is the formulation we use to find the energy eigenvalue for the wave function. So psi n is the wave function we already studied. So this is the formula in which we put the values and get our result. These values are very simple. We already studied in detail. The quantity alpha sets the scale of energy. For example, when we put all these values, this shows that alpha n square. So alpha is the set of scale of energy, which tells us about the energy and its change in energy value, upgrade or downgrade. Then we will study about the alpha. For an electron in a length of 1 centimeter, the value of alpha is. So now we will find the energy. This shows that the energy alpha is the energy, and we put all the values, constant values, and get the result on the in term of temperature. So our answer will be this. So in this way we can find the energy of a particle in one dimension.